Hello everyone. It's my pleasure to talk about how Uber leveraged Pinot to power the real-time business insight. Today, I'm going to talk about the Pinot partial upsert feature that contributed by Uber. On the second part, I'm going to talk about some Pinot upsert optimization by Uber. So about me, my name is Qiaochu Liu. I'm a staff software engineer at Uber, and I work for the real-time analytic platform that leverages Pinot to power the real-time critical business insight at Uber. So first, we want to take a look at Pinot at Uber. Pinot is a fast, reliable, scalable solution to power the real-time insights, including the exploration, visualization, and actions. We want to empower the user-facing application with low latency and optional data freshness. There are a few interesting numbers that we powered at Uber. So first, we are supporting high QPS, like 15,000 query per second globally. Second, we can provide low latency for both ingestion and the query. We provide less than 30-second data freshness, and majority of our query can finish within 100 milliseconds. We provide less than 100 millisecond P99 query latency. To get your data into the real-time analytics storage at Uber, there are two kinds of data sources. The real-time data coming from the Kafka and offline data coming from Hive table. We are building an internal self-serve onboarding platform that can easily onboard the Pinot table using a UI. And for the query side, we are supporting the Presto SQL for the query analysis. The Presto to Pinot connector is also contributed by Uber. We provide multiple BI tools to integrate with the user's use case, and we can also allow users to build their own UI. There are many 4 categories of use cases that we support at Uber. First is the user-facing apps. Second is the external analytics, like dashboarding. And third is operational excellence. For example, there may be some data scientists, CTOps, they are using our platform. First, we also provide the ad hoc explanations to get the analytical insight of the user's data. So this image shows a very interesting use case from the Uber Ads data flow. So the user's click impressions are collected from the Uber app, and then after streaming processing via Apache Flink, this data will ingest into the Apache Pinot and power the key insight metrics for the building, analytic, pacing metrics. This use case is interesting because these clicks, the impressions data can change, and user may want to know the most recent real-time view of their data instead of the historical view. So this use case is using the Pinot Upsert feature. Now let's talk about the Upsert. So why Upsert is important? So Upsert means the real-time updating of existing record. And by nature, the data can be updated or corrected. And customers, they may want to know what is the updated view of their data. And there's no easy SQL workaround to express this Upsert logic. However, we may have other use case scenarios because the current full Upsert only support the full override of the existing record that share the same primary key. But there might be some use case scenario. For example, for we have a driver file use case, and each of the records from the Kafka topic indicate a fair adjustment to the existing rider. So what we can do is we cannot use the full Upsert feature because we do not want to override the historical data. Instead we want to append this new value on top of the previous value. So we want to merge the previous record and the new record properly. Another example is that we may have some missing field in a Kafka topic, and we have the later event to fix and fill this kind of missing values. However, each fix may only contains one column or one field. We have to have more than one later event to fix all the missing values. And if we are using the full Upsert, every time we will update the existing record, and then we will never fill all the missing field. So these are two new requirements that make us build this partial Upsert feature. For the partial Upsert, we have some new requirements. First, we want to specify the column that value need to be changed and ignore the other values. And second, we want to support different merge strategies and maybe more complex merge strategy than the override. So there are list a few Uber's use case that powered by Pinot Upsert feature. Uber Eats, tech, customer obsession. This is because the orders, fares, rider status can change. So these are very suitable use case for Upsert. Next slide, I'm going to talk about the full Upsert before we talk about the partial Upsert. So I borrowed this slide from Yupeng, amazing talk from Yupeng last year. And in this slide, I want to emphasize that in the Pinot real-time ingestion flow, the real-time data are grouped in a unit called segments. And segments are distributed to multiple servers, so we can run the query parallelly and avoid the bottleneck of single server. And each segment may have multiple replicas, so if one server is down, we can still serve the query and without missing the data and unavailable segments. However, these segments distribution allocation are provided challenging for the Upsert feature because we need to figure out the previous record that share the same primary key and how we're going to update the existing record. So Yupeng proposed the local key coordinator approach to make sure the same primary key will always appear on the same server, so the upsert can happen efficiently. And it also leverages the partition by key feature in Kafka. And Pinot is actually the first ever OLAP engine that supports the upsert feature. Now let's talk about this local key coordinator approach. We can see the architecture of the local key coordinator approach. We have two in-memory data structure to keep track of the upsert metadata and validDocIndex. We also introduced the multiple different components. For example, the first one we introduce a local key coordinator to track the primary key to record location mapping. Second, we have this bitmap to store the validDoc or skip the doc that are no longer the latest record, so they will be filtered during the query. Third, we also have the stream ingestor to update the upsert metadata during the ingestion. The upsert metadata include both invalidDoc step ID and the primary key to record location mapping. Next is that we have the query executor to filter out the skipped docs. Last but not least, we are dispatching the query to the same server for the segments of one partition. So in this graph, we can see how the stream ingestor processes the incoming message. If it is a record that does not share the primary key with the existing record, then we will just do an insert. And if it is a existing primary key, we will check the time and see if it is a late event. If it's a late event, this message will be skipped. If it is not a late event, then we will compare if this if the validDoc is appear in the current segment or in a previous segment. If in the current segment, we will just update the validDoc index. But if it's in the previous segment, we will have to remove it from the previous segment's validDoc index and add to the new segment's validDoc index. After the full upsert overview, we can talk about some new component from the partial upsert. So the partial upsert, during the design phase, we have like two approach. So the first approach is like track the full history of the update, identified by the same primary key, so that we can backtrace the series of updates and fully merge the result during the query. And this approach keeps the modification in the original form of the record. However, it is a complexity during the query time, and also it is the additional metadata. So it will be less performant during the query time because we may need to scan a lot of segments to find out all the existing record, and we may take some time to merge the result and return to user. Another approach is we can derive the full record during the ingestion time. Each time we ingest a partial update, we will apply this update to the previous record and get a full derived column. And every time when we ingest a new record, we do not need to make any change, and we just need to look up the latest event. And that latest event, we will perform a merge on top of that and get another fully derived column and make this field, make this record as the latest event. So this approach is relatively easier to implement and more performant during the query time. So we introduced two new components in this partial upsert architecture. The first one is the partial upsert handler, which initializes a series of mergers for each of the column. Another component is called merger. So merger handles the merge of the previous full record and the new consumed record with different strategy on different columns. So we can also specify the merger at the table level, a global merger. We are also supporting that. So this is an example of the partial upsert merger config. So we can specify a global merger, and it will be used for every column that is not specified. And we can also specify the merger at the column level, and they will override the global merger. These are the mergers that we currently supported. Let's take a quick example. In this graph, you can see there's an override column, ignore column, append column, increment column, and a union column. Each of the columns represent behavior of the merger. The assumption before we get started is all of these records have the same primary key, and they have the timestamp, which is in ordered timestamp. So the second record will be merged with the first record, and third record will merge with the first and second record. So when the second record comes in, for the override column, it will override the latest value. And for the ignore value, it will not override the existing earliest value. For the append, it will append the new value into the multi-value field. And for the union, it is an improvement of the append merger. It will append the value if the value is not exist. So it also does the dedupe work. And last but not least, we have an increment merger, which is suitable for the rather fair use case that we previously talked about. We are adding the new value to the existing value. So these are examples for the upsert mergers. So that wraps up the partial upsert. Let's talk about some upsert optimization made by Uber. So first, we have a primary key compression with hash function improvement. So as we know, we store all the upsert metadata in memory, and it can be a bottleneck for the upsert server. So what we can do is we recommend the user to use a simple primary key type and avoid the composite primary key, so that will save a lot of memory cost. In addition, we can also consider using a hash function config in the upsert config. This config provides you the option to use the MD5 or more 3 to store the 128 bits of hash code of the primary key instead of store the primary key itself. And this is useful when your primary key takes too many space. But the hash function, there might be something we need to keep in mind. There is a very low possibility to introduce collisions. Another example that I just want to talk about is also the comparison column. It's also shown in this example. Comparison column is something that we want to use it to determine the latest event. And by default, Pinot uses the value in the time column to determine which one is the latest record. And that means for two records within the share the same primary key, the record with larger value of the time column will be picked up as the latest update. There might be use case they are saying, oh, we want to use another column as a time column. We do not want to use the time column to control the override and upsert. So they can set up another time column as a comparison column and use that column to determine what is the order of the event. So in this kind of scenario, you can say you have a different column, you can specify it as the comparison column and override the column used for the comparison. So we can also disable the upsert feature on the fly for the troubleshooting or auditing. So you can use the skip upsert in the query to see the difference from the append-only table and compare this result with the upsert table for troubleshooting. And you can use the query option skip upsert to skip the upsert effect in the query result. However, for the partial upsert table, this is different because it's no longer stores the exact partial update information in the segments. As a result, there might be some challenging for the auditing, debugging, and troubleshooting because all the record that we store in the segment is already merged. And if you want to trace the original update, we can have some improvement on the vertical column. We can store the Kafka offset or the original change in the vertical column. That can be one improvement we can do in the future. Last but not least, I want to talk about this ongoing project at Uber. We are supporting the TTL for the primary keys. Yeah, as we know, we have the primary key stored in memory, and it becomes a bottleneck for the Upsert table. And we want to optimize the table that has large numbers of a unique combination of primary keys. It's hard to store all this large amount of primary keys in memory, especially when there are some of the primary keys that is not updating anymore. So for table record with specific primary keys that will get updated frequently during a time window, there might be some example. And after this time window, this primary key will never be updated. For example, we may have a Uber trips status table, and the event are updated like when it's assigned to a driver, and then pick up, and then on trip, and then drop off. And then the status will never be changed because the trip is already complete. So for this kind of use case, if the table retention is very long, for example, like 1,000 days, but the life cycle for each of the primary keys is only 3 days, then we are keeping a lot of actual data in the memory. So what we can do is we introduce this TTL support for the primary keys. So we want to introduce the TTL support, and if the primary key is after the life cycle, after it's expired, we will just remove it from the primary key metadata. So we will not use a lot of memory. We will only keep the TTL time in for the primary keys in the memory. However, there might be some challenges. It's very common that the segment can be rebuilt, the server can be restarted, and sometimes the in-memory data structure can be lost and need to be rebuilt, the primary key index and validDoc indexes. So when we rebuild the validDoc index, it was inferred from the primary key index. And with this TTL support, we actually lost track of some historical expired primary keys. And how are we going to recover the validDoc index? We will introduce another index called validDocSnapshot to periodically persist the snapshot into the disk. And we can recover the in-memory metadata quickly using this validDocSnapshot. So if you're interested in this TTL support, please take a look at our design doc. The design doc is attached in the slide. That's all the content that I want to share today. Thanks for inviting me to present at the Real-Time Analytics Summit. If you have any questions about Upsert, partial Upsert, Upsert optimization, or Pinot at Uber, please feel free to reach out to me. Thanks for joining the summit. Thank you.